this point, we're going to kind of pause for a moment in our study of integration to go back and review some of the processes that we learned for taking limits, and then also to add a new one called L'Hopital's rule. Depending on your Calculus 1 experience, you may have done some things with L'Hopital's rule already, but I'm going to treat it like a new topic because it's not formally part of our Math 151 at Jackson College. So first of all, I wanted to mention that in your course pack, this review of limits is there, and this I'm not going to take the time to do. These are all the types of things that you did back in Calc 1. And they're in the filled out portion, so my suggestion might be that you go ahead and try these, see if you can remember the techniques for taking limits, and then check your answers and look up how to do the ones that you don't remember. And then we're going to spend a little time here together today talking about another method for limits called L'Hopital's rule. Once we have these limit techniques in place, in the next section we'll be able to go back to our study of integrals and see where these limits come into play. So a little bit of time for review because it feeds what we need in the next section. Okay. The limits that we're going to be focusing on are the ones that are what we call indeterminate forms. These are the ones that when you start and you try to plug in your value, like if I plug the 5s in here, come out 0 over 0, or the other one that we already have studied a bit in Calc 1 are the ones that come out infinity over infinity. It turns out there's actually many more indeterminate forms, and indeterminate forms in general are what we're going to talk about for L'Hopital's rule. This was actually covered in section 4.7 in your textbook, but as I said, we kind of skip over it in Calc 1, and we're going to go back and pick it up right now. So, again, with working with limits in the past, we've always noticed that the case 0 over 0, we can often do enough algebra to result in a finite limit, and similarly for infinity over infinity. 0 over 0 and also infinity over infinity are one of several types of indeterminate forms. We're now going to learn that we can use calculus to actually help us find limits in which this and other indeterminate forms are part of the problem. All of these are actually indeterminate forms. And we're going to take a look at all of them in this section. But I'll have you notice that essentially that whole idea of indeterminate form means that the form can actually turn out to be literally anything when you find the limit. You've seen this a number of times, right? Here just on this first page, 0 over 0 turned out to be 1 over 2 square root 5 on this problem. 0 over 0 turned out to be 0 here. And it turned out to be negative a half there. And there's lots of others as well. Any indeterminate form, any of these can, just like the examples I just showed you, turn out to have any value. And we have to go through a process to figure out what that value is. Right? So I'm going to start introducing this theorem called L'Hopital's rule. L'Hopital's rule specifically refers to the two indeterminate forms, 0 over 0 and a form of infinity over infinity. If I have these others, we'll have to use some other techniques, but we're going to start with these two and what's called L'Hopital's rule. Here's a statement. If the limit of f and the limit of g are either both 0 or both infinite, then the limit as x goes to a of f over g is the same as the limit as x goes to a of f prime over g prime. So what this says is if you get one of these two indeterminate forms to start out with, try taking derivatives on the top and the bottom and see if that helps you with your limit. Let's try a few problems using L'Hopital's rule. I'm going to notice here this limit as x goes to 0 of sine x over x. Sine of 0 is 0, and in the denominator x is 0. So this is a legitimate problem in which L'Hopital's rule could be used. I've got one of the two acceptable cases. 0 over 0, or infinity over infinity. In this case, we've got 0 over 0. So what I'm going to do is I'm going to say this is equal to the limit as x goes to 0. And this is where I use L'Hopital's rule. I'm going to just kind of denote that by saying this step uses L'Hopital's rule. And now I'm going to take the derivative. So the derivative of sine x is cosine x, and the derivative of x is 1. Notice we definitely don't have 0 on the bottom anymore, so that's a really good thing. Let's go ahead and try plugging in. We would just get cosine 0 over 1. That's 1 over 1, or 1. Okay. Now, you probably recognize this right off the bat as one of our special limits. When we looked at it back in Calc 1, we actually did this one numerically to get this answer. But you can see with L'Hopital's rule, we can get there pretty quickly, and we don't have to plug in a whole bunch of numbers. Right. Let's try a couple more. This next one, as x goes to infinity, the top becomes infinite, and so does the bottom. So this is the infinity over infinity case. Again, one of the two cases where L'Hopital's rule applies. So I'm going to go ahead and do my L'Hopital's rule step. The derivative of the top, 6x minus 6, and the derivative of the bottom, 10x plus 1. Now, if I think about x going to infinity, that still becomes infinitely large, and so does that. So I still have infinity over infinity. I still have a problem that could be addressed by L'Hopital's rule, so I'm just going to do it again. Derivative of the top is 6, and the derivative of the bottom is 10. And so I just get 6/10 or 3/5 for my limit. Don't even have to plug anything in, right? By the way, notice that's consistent with that ratio of the leading coefficients that we would expect when the powers are the same. All right, let's try a few more. It's important to always verify before you start that L'Hopital's rule applies. So let's make sure here. This one would be e to the 0 minus 1 over 0 squared plus 0. That's 1 minus 1 or 0 over 0. So yes, L'Hopital's rule does apply. So we'll go ahead and do it. I've got the limit as x goes to 0, and the derivative on top is just e to the x. The derivative on the bottom is 2x plus 3. If I now plug in the 0, I'm going to get e to the 0 over 0 plus 3, which would be 1/3. Pretty slick. This often works really well. Couple more. In number 4, as x approaches 2, the top would be 4 plus 2 minus 6. The bottom would be the square root of 8 minus 4, and then minus 2. 0 on the top. Square root of 4 minus 2 is 0 on the bottom. So yes, I do have the indeterminate form 0 over 0, and L'Hopital's rule does apply. So I'm going to apply L'Hopital's rule, take derivatives of the top and the bottom. Derivative on top would be 2x plus 1. And the derivative on the bottom would be 1/2, 8 minus x squared to the negative 1/2, times negative 2x for the chain rule, and then minus 1. If I go ahead and try and plug in my 2 now, the top would be 4 plus 1. And on the bottom, those 2's will cancel. So I actually would have a negative 2 over the square root of 8 minus 4 minus 1, which is going to give me 5 on top. And let's see, that's negative 2 over 2 minus 1. Minus 1 is negative 2. So I end up with negative 5/2 on that one. And of course I could have plugged that 2 in with a calculator if I wanted to as well. Just playing with the arithmetic here today. All right, one more fairly straightforward one. As x goes to infinity, the natural log of infinity is infinity. And again on the bottom, natural log of infinity is infinity. So I do have one of those L'Hopital's rule cases. Again, it's got to be 0 over 0 or infinity over infinity. But it is. So we're ready to apply L'Hopital's rule. I take the derivatives, top and bottom. And let's see, on the top I'd get 1 over 3x plus 5 times 3 for the chain rule. And the bottom, 1 over 7x plus 3 times 7 for the chain rule. And let's see, the top is actually 3 over 3x plus 5. I'm going to take the reciprocal and multiply for the denominator, so that would become 7x plus 3 over 7. Multiplying this out, I'd have 21x plus 9 on top and 21x plus 35 on the bottom. Now notice as x goes to infinity, that's still infinity over infinity. And so I'm going to go ahead and apply L'Hopital's rule again. Derivative on the top is 21, and so is the derivative on the bottom. So I just end up with 21 over 21, or a limit of 1. So when you start with one of those forms, 0 over 0 or infinity over infinity, it's usually at least somewhat straightforward to go ahead and calculate your limits. Now let's take a look at what happens when we have other indeterminate forms. Again, really important to note, L'Hopital's rule only applies to the forms 0 over 0 and infinity over infinity. Okay. If I have any other indeterminate form, I have to convert it to one of these before I can use L'Hopital's rule. Right now, we're going to go ahead and we're going to look at the form 0 times infinity, which is indeterminate, and infinity minus infinity, also indeterminate. And we're going to say, because they're indeterminate, my best bet is to try to convert them to one of these and then use L'Hopital's rule. As it says, typically this is going to involve converting one of the factors to division by the reciprocal. Let's give it a shot. Right here, we've got, let's see, if I try to plug in, I would have 1 minus 1 times the tangent of pi times 1 over 2, or just pi halves. Of course, that's 0. And tangent pi halves, if you're not sure, just take a look at a graph. Let's see, I'm going to put my window as negative pi to pi with a scale of pi halves. And what I'm going to have you notice here is the pi halves then would be right here, right? And tangent is going to plus or minus infinity right there. That's a vertical asymptote. Now, since my limit is going from the left, I'm going to say tangent goes to positive infinity from the left. So tangent of pi over 2 is infinite. So I do have my 0 times infinity case, which is one of the indeterminate forms. It's kind of a conflict between anything times 0 is 0 versus anything times infinity is infinity. Which way do we go? Well, it turns out that the answer can actually turn out to be anything, and we'll find that out in a moment. All right, that's great. I know it's indeterminate. The problem is right now, because it's not one of these forms, I can't apply L'Hopital's rule yet. So I'm going to rewrite. In order to do L'Hopital's rule, I have to have a quotient. I have to have something top and bottom. So I'm going to start here by rewriting. And I'm going to leave the 1 minus x on top. And if I put the tangent on the bottom, the reciprocal would be cotangent. Now what happens if I try and plug in the 1? Well, the top is 1 minus 1, and the bottom is the cotangent of pi over 2. Numerator is 0, that's a good start. And the cotangent of pi over 2, if I do the cotangent, which would be 1 divided by the tangent of x, and graph that, same window. So there's pi over 2. Looks like at pi over 2 we have 0. So still an indeterminate form, but the advantage is this is a form that I'm allowed to use L'Hopital's rule on. So here we go. Limit as x approaches 1 from the left. The derivative on the top would be negative 1. And the derivative on the bottom would be negative cosecant squared pi x over 2 times my chain rule would give me just a pi times 1 over 2, or pi halves. All right, let's work with this a little bit. Negatives will cancel out, so I can just forget about those. And I'm going to use some reciprocals. Cosecant is the reciprocal of sine, so I can move this to the top if I make it sine squared pi x over 2. And dividing by pi over 2 is the same as reciprocal times 2 over pi. So basically I moved both of those terms into the numerator by taking their reciprocals. Now if I try to plug in, I would have sine squared pi times 1, or just pi over 2, times 2 over pi. Sine of pi over 2 is 1. So I just get 2 over pi for my limit. All right. L'Hopital's rule is great. Helps us in a lot of situations. But there are times where the methods that we already know are actually more efficient. And example 2 is actually here to show you that kind of situation. Okay. So we've got the limit as x goes to infinity of this expression. And first of all, I'll point out that if I tried to plug in infinity, x is going to infinity. And under the radical, x is also going to infinity. So this is the indeterminate form, infinity minus infinity. I know that it's indeterminate, but not yet one of the two forms where I can use L'Hopital's rule. So we're going to play around with this a little bit. And I'm going to use a very common trick when you've got radicals like this. We often use multiplying by the conjugate. So I'm going to rewrite the original problem and just put 1 in the denominator. And then I'm going to multiply by the conjugate. Top and bottom, just multiplying by a form of 1. So on top, x times x is x squared. Outers and inners will cancel. And then I get subtract this quantity, x squared minus 3x. The bottom is just x plus the square root of x squared minus 3x. Okay. Numerator, of course, x squared minus x squared is 0, and then I'll end up with a positive 3x. I'm sorry. No, I did that right, yeah. Positive 3x. And then the denominator, x plus the square root of x squared minus 3x. Okay. So, what have we got here? At this point, as x goes to infinity, 3 times infinity is infinity on the top. And on the bottom, we've got infinity plus infinity. Infinity plus infinity is infinity. So I've finally got a form where I can use L'Hopital's rule. All right, the derivative on the top is just 3. And the derivative on the bottom is 1 plus 1/2 x squared minus 3x to the negative 1/2 times 2x minus 3 for the chain rule. So in the denominator, I've really got 1 plus 2x minus 3 over 2 times the square root of x squared minus 3x. And here's my problem. The 3 is fine, the 1 is fine, but notice this little sub-problem right here. What about this fraction? Well, that's still infinity over infinity. If I continue to do L'Hopital's rule again and again, what's going to happen to that little piece is this radical is going to keep going from top to bottom to top to bottom. And because of the chain rule, the 2x minus 3 will be on the other side of it. So this is going to get me into sort of an infinite loop. With L'Hopital's rule. I'll continue to get that infinity over infinity over and over and over again. So because of that, I'm going to say, you know what, it was worth a try, but I think I'm going to abandon this. I think L'Hopital's rule is not going to get me where I want to go this time. Instead, the more efficient method is to actually just go back to what we learned in Calc 1 this time. When we have infinity over infinity, dividing through by the highest power of x was a good option, right? So what if we just go back to that? If I've got my limit of 3x over x plus this radical, and I just divide it by x over x. The numerator becomes 3. The denominator is 1 plus, and then under the radical, dividing by x is the same as dividing by x squared under the radical. So that becomes 1 minus 3 over x. Now as x goes to infinity, I have 3 over 1 plus the square root of 1 minus that fraction as x goes to infinity is 0, or 3/2. Much simpler and gets me to where I need to go pretty quickly. So, moral of the story is L'Hopital's rule is great, but there are still times where you're going to find the Calc 1 methods are the most efficient. All right, last but not least, let's look at the indeterminate forms that are exponential forms. The forms 0 to the 0, infinity to the 0, and 1 to the infinity. All indeterminate forms, so they can be anything, but not L'Hopital's rule forms. So forms that, again, I would like to get to become L'Hopital's rule so that I can do them more efficiently. Let's take a look. There's a little note here. I actually don't do it this way anymore, so I'm going to say just ignore that. I'm going to show you what I think is a slightly more understandable method, or at least that's what students have told me over the years. I started doing things a little differently, and people seem to follow them better. So, first of all, this first problem, I've got x to the 2x as x goes to 0 from the right. If I plugged in the 0, I would certainly have 0 to the 0 power, which is an indeterminate form. Again, it's kind of a war between 0 to any power is 0, and anything to the 0 power is 1. Which is it? Well, it's not necessarily either one. It's an indeterminate form. All right, I need to get this to either look like 0 over 0 or infinity over infinity. And the way I always deal with the exponential forms is I take the natural log on both sides. So what I do is I start by saying, right now there's not two sides, right? There's not an equation. So I'm just going to say this limit that I want to find, let's define it. Let's call it L. L for limit. And now I can take the natural log on both sides. The natural log of L equals the limit as x goes to 0 of the natural log of x to the 2x. Why is this an advantage? Well, remember the rules for logs say I've got that property, a power property, that allows me to bring the 2x down in front here. So I'd have 2x ln x. And what's going on now? Well, let's see. As x goes to 0, 2x would become 0. And what happens to the natural log function as x goes to 0 from the right? Coming towards 0 from the right, natural log looks like it's going down to negative infinity. If I change my window just a little bit to show more negative y values, we can see that even better. Yeah, there's that ln graph goes down to negative infinity as we go towards 0. So I started with the indeterminate form 0 over 0. I've now got a different indeterminate form, 0 times negative infinity, but it's still not a L'Hopital's rule form. The biggest part of this problem is I don't have a fraction yet, right? L'Hopital's rule is going to be impossible unless I have a fraction. So let's see if we can create a fraction now. Not a whole lot I can do with that ln x, so I'm actually going to leave the 2 ln x on top. And I'm going to move this x to the denominator and make it an x to the negative first. All right, now what have I got? Well, let's see. As x goes to 0, we've already said natural log x goes to negative infinity. And what about this? X to the negative first. Probably should change my window. I'm going to do a zoom standard. Here we go. As x goes to 0 from the right, looks like this goes to positive infinity. So I'm finally there. I've got an infinite over an infinite. The signs don't matter. I can finally use L'Hopital's rule. So, L'Hopital's rule. From here, I would have the ln of the limit, natural log L, equals, the limit as x goes to 0 from the right, and the derivative on top would be 2 times 1 over x. The derivative on the bottom would be minus x to the minus 2. So I've got, let's see, let's be consistent. Let's just call that 1 over x, x to the negative first. And then that minus sign, I'm going to just divide that out, make that a negative 2, and I'm going to move that x to the negative 2 to the top and make it x to the positive 2. So I've got negative 2, and that would just be adding the exponents, x to the first. And if I plug in 0, I'm just going to get 0. Now that's not my final answer yet, right? That's not the limit I wanted. That's not L. That's the natural log of L. So one more algebraic step here. If I just exponentiate on both sides, e to the ln L equals e to the 0. L is actually 1 for my final answer. Easy to forget that last step. You get so excited when you get a limit that actually works, right? But don't forget, on all of these exponential problems, you're always going to start them with a natural log. So at the end, you'll have to get rid of the natural log by exponentiating. All right, let's try one more like that to finish out this section. We've got the limit as x goes to infinity of 1 plus 1 over x, all to the x power. If I were to plug in infinity, so to speak, I'd have 1 plus 1 over infinity, that would be 0, to the infinity power, or 1 to the infinity, which again is one of our indeterminate forms. It's an exponential form, and so my sort of default mechanism is anytime I see these exponential indeterminate forms, I want to start by defining the limit as L and taking the natural log on both sides. So if I say this is L, then the natural log of L is the limit as x goes to infinity of the natural log of 1 plus 1 over x to the x power. Same deal as before. I'm going to use that power property of logs to bring this x down. Like so. And then let's look at what's happening here. As x goes to infinity, this x becomes infinitely large. And let's see, that would be the natural log of 1 plus 0. So I have infinity times ln1, but ln1 is 0. So I still have an indeterminate form. It's just a different indeterminate form. Okay, we can handle that. Just like last time, I'm going to say right now I've got a product. My goal is to use L'Hopital's rule. I need a quotient, need a fraction. So let's do a little rearranging. Hard to do anything with the natural log. I'm going to leave that where it is, and I'm going to use the exact same trick as last time. that x, I'm going to move to the denominator and make it an x to the negative first. Now this natural log of 1 or 0 is on top. And as x goes to infinity, x to the negative first is 1 over x, right? 1 over infinity is also 0. So I've got the 0 over 0 case, and I've finally got something where I can use L'Hopital's rule. So ln of my limit L is equal to the limit as x goes to infinity. And here's my L'Hopital's rule. The derivative of the top would be 1 over 1 plus 1 over x times, chain rule, I have to take the derivative of what's inside here. Derivative of the 1 is 0. That's really x to the negative first. So minus x to the negative second would be its derivative. In the denominator, I've got x to the negative first, so minus x to the negative second, its derivative as well. And that couldn't have hardly worked out better, right? Those, of course, can be divided out. All right, as x goes to infinity, I'm going to end up with 1 over 1 plus 0 for that fraction. So the natural log of my limit is just 1. And once again, I got to get rid of the ln. I want to know what L is. So if I exponentiate on both sides, L is e to the first, or just e. All right, that brings us to the end of our section on finding limits by L'Hopital's rule. We'll be using these techniques for finding limits as we do some new kinds of integrals in the next section.